This is 2021 paper 2 question 6. So we have two triangles and they're similar. I want to prove that their sides are proportional in order. So in terms of our diagram, we have a triangle ABC. So if we draw that out, you can say this is ABC. And we can say that this angle, we can label this angle and this angle with 3 lines. And we're going to have another triangle, call it A prime, B prime, C prime. And they're similar. So their angles should be the same, but their side lengths aren't going to be the same. So we're going to have, here's A prime, here's B prime, and here's C prime. And as you can see, we're labeling the angles as the same. So I've just slightly redrawn this. So we have ABC, we have A prime, B prime, C prime, and then I've drawn this new triangle, which I'm going to get to in a second. So in terms of filling in the information given, that's just the information we're given. So you're kind of copying this from the question. We have triangles ABC, and we have triangle A prime, B prime, C prime, and they're similar. What are we trying to prove? Again, it's given in the question that their side lengths are proportional in this order. The construction we're going to do then is, right, we have these two separate triangles, and we know their angles are the same, so it would help if we overlap them. But I suppose you could technically say that we translate this over, but the way that's generally recommended is that we're going to construct. So we're going to take our triangle ABC, we're going to construct 2 points on it. We're going to have B double prime and C double prime, and I'm just calling them that so that they're easy to follow. So B double prime, we're constructing B double prime such that the length AB double prime will be equal to the length A prime B prime. So essentially what our goal is here is we're trying to draw this smaller triangle on the bigger triangle so that we can investigate some stuff. So our first step is we're drawing the side A prime B prime, and on our new triangle we're drawing we're putting in this point B prime so that we have A B double prime is the same as A prime B prime. Okay, so we're basically drawing in this side, which is the same as this side, so we're drawing in the smaller triangle. And then similarly, we're going to draw in C double prime such that the length A C double prime will be equal to the length A prime C prime. So again, we're drawing in this length here, which is the same as this length of this triangle. And we're not like implicitly assuming that B double prime C double prime is the same as B prime C prime, because we can't assume that. In geometry, it's important that we prove everything from the ground up. So how are we going to prove that this new triangle is actually the same as this triangle? Well, we can do it by congruency. So in terms of our proof, what we're going to say is we're going to prove that this triangle is congruent to this triangle. So how are we going to do that? Well, we know that A B double prime is equal to A prime B prime. And that's kind of in the construction. And similarly, we just defined AC double prime to be the same as A prime C prime. So again, that's in the construction. And then we also know that the angle B prime A prime C prime, so that's this angle up here, will be the same as the angle, we're going to say B double prime A C double prime. So we're going to have B double prime A C double prime. And why is that? Well, because we're told that these two triangles are similar, right? So that means that this small angle up here has to be the same as the angle at the top of the big triangle. So that's because triangles ABC and triangles A prime B prime C prime are similar. Okay, so therefore we have a side, we have two sides, and we have the angle in between them. So by side angle side, we can say that A B double prime C double prime, so the triangle A B double prime C double prime is congruent to the triangle A prime B prime C prime. Triangle A prime B prime C prime. Cool. So now we've proven that this new triangle that we drew in is the same as this smaller triangle here. So what that means is this is the double angle, which is the same as this double angle, and here we have the triple angle, and here we have the triple angle, and then I should have drawn this in from the start. Okay, so basically we see that these two angles are the same and these two angles are the same. So when you see two angles that are the same and they're cut off by these two lines, that tells us that those lines are parallel. So because you might remember the thing with the z's, so if you have like these z's and if we have corresponding angles like this angle and this angle, it goes both ways. So if these two lines are parallel, that means that this angle is the same as this angle, or conversely, if we know that this angle is the same as this angle, that means that these two lines must be parallel. So that's basically the fact that we're going to use here. So we're going to say that the two lines, so B double prime and C double prime is parallel to BC. So B double prime C double prime is parallel, which you can write with these two lines, to BC, and that's because, why is that? Well, it's because AB double prime C double prime is the same as ABC. So the angle AB double prime C double prime is the same as the measure of the angle ABC. So yeah, they're basically corresponding angles. You might want to write that in. Cool. So now that we know that these two lines are parallel, we can use another theorem. There's lots of theorems to do with two parallel lines. And one of those theorems is that they kind of cut off lines in the same ratio. So that means that the ratio that this side is cut into is going to be the same as the ratio that this side is cut into, and that's because these lines are parallel. So I suppose what you could say then is since these are parallel, we can say that AB is cut in the same ratio as AC over here. AC. So there's a few different ways you can say that. So that means that AB double prime divided by B double prime B is the same as AC double prime over C double prime C. But what we're looking for really is that this is our smaller triangle and AB is our bigger triangle. So what we want to say is that AB divided by AB double prime is the same as AC divided by AC double prime, because that's the sides of the big triangle divided by the sides of the small triangle. So what we can say is that AB, so therefore AB divided by AB double prime will be equal to, and then we have the length AC divided by AC double prime. So we're going to say AC over AC double prime. So that's the first part that we wanted. That's up here. So we have AB over A prime B prime, and then we have CA over C prime A prime. So I suppose this isn't exactly what we wanted, but we know from our construction that A B prime is the same as A prime B prime. So we might replace that just because we want to prove exactly what we said up here. And this isn't exactly what we said. So we can say, therefore, we have AB divided by, and AB double prime is the exact same as A prime B prime, right? From our construction, this side was going to be the same as this side. So the reason we have to do that is because this isn't technically our original smaller triangle. This is like a copy of it that we drew in. So just to state it very explicitly, this is AB over A prime B prime, because it's the same length, which is equal to AC over A prime C prime. And now you might be wondering, how about the last part? So we have AB, we have AC, we don't have the BC over the B prime C prime. Well, essentially what you'd have to do is, you see how I've drawn this triangle up in the top? What you'd have to do is you'd have to draw the triangle in the bottom right, and then you get another, okay, wait, let me draw this out, it'll be easier. So what you technically have to do is you have to do it this way, and then these two lines are going to be parallel, and then we have these sides are in the ratio of these two sides, but you don't have to do that. What you can just say in the exam is you can just say similarly, as in like we can prove it in a similar way, that we'll have AB over A prime B prime, and then what's the side we haven't done? We didn't do the side C. So here we have AC and BC, so we didn't do the sides with BC, right? So we can say similarly, we could do a similar method to do AB over A prime B prime will be equal to BC over B prime C prime. So that's just saying we can do a similar method to prove that. And we can say hence, as in completing our proof, because we've done all the work now, we just need to say, well, what did we set out to prove? Have we proven it? Well, we have. Well, we've proven that these ratios are equal, and then since this ratio is equal to this ratio, which is here, these ratios must also be equal to that. So yeah, that's just kind of like a big chain of inequalities. So we have all three of these ratios equal to each other. Then we have to prove that this product is equal to this product in this thing. So it might seem weird how we're going to prove a fact about products, but really what products are just ratios but rearranged. So what we notice is that we have AH and we have AP. They kind of have a side in common. And then QB and HB also have some sides in common. So what might help is if we rearrange this. So we can say that AH divided by AP will be equal to, and then we're going to have HB divided by QB. And now this looks more kind of similar to what we kind of used to proving. And this could have something to do with similar triangles because we have sides that are in ratios with each other. So let's just have a look at what's in question. So we have AH and AP. So we have AH, I'll do this in red. I'll try to do it in a straight line. We have AH and we have AP. So we might consider looking at this triangle for that reason. And then also we have HB. We have HB we have HQ, or sorry, we don't have HQ, we have QB. So we have QB, which is this side, and then you can see to finish off that triangle, we might want to do HQ. So now you can see it's a lot more clear now after we've kind of done that deduction that these are two triangles in question. And if we could prove that they're similar, well, then their sides are in the same ratio, and then we just basically get the answer. So this is what I'm going to keep in the back of our minds. Let's see if we can prove that they're similar. Well, clearly we can see some vertically opposite angles. So we can see that the angle BHQ, and I'll draw this in on the diagram now actually. So this angle and this angle, they're vertically opposite. So BHQ will be equal to the angle PHA, and that's because they are vertically opposite. And it's important to use all the information a question gives you. So we're told that they're all the PA, so that's this, and then we have HK, this, and BR, which is this. They're all parallel. So when we have parallel lines, we can do some nice things with alternate angles and such. So what you might notice is that we have this angle here and this angle here, and you can see they kind of make a Z. So this is on the right side of the Z, and this is on the left side up at the top. I might draw that in pink just to try to make it a little more clear. So you can see we have this big Z here, and we have our alternate angles. So we can just say that the measure of angle PAH will be equal to the measure of angle, and then we're going to have HBQ. And that's because they are alternate angles. And then we get the third angle for free. So we can say that the third angle in each, or I guess we could say the third angle in, just to be very clear about it, triangles HBQ and triangle PAH are the same. And that's because all three angles sum to 180 degrees. So if we know two of the angles, we can get the third angle, and we already know that two of the angles are the same. So in order for them both to add up to 180, the third angle must also be the same. So we can say that therefore triangle HBQ is similar to, so you can use this sign if you want, or you can just say is similar to triangle PAH. So we can say therefore their sides are in the same ratio. So what we wanted to remember was AH over AP, so that's AH over AP. So it's probably not a good idea to use those ones, because you should be, I mean, you can, it's all the same thing, but you should really be saying the corresponding sides on each triangle. So if you imagine rotating this triangle around such that the red angle is down there and the pink one's matches up here, then what we would have is we'd have this triangle BHQ, and we'd have a bigger one, which would look like, so the red angle here, where B is, that's where A is. So A is going to be down here once we rotate it. H is where the pink angle is. And the pink angle, when we rotate it, it's going to be up here. So that's going to be H. And then Q is just the last one. So this is going to be P. So Q is the unlabeled angle here. So P is going to be the unlabeled angle in this triangle. So now their sides are going to be in proportion. So what are we looking at? We're looking at AH, which is this side, and HB. So that means that AH divided by HB, so that's two corresponding sides. These two sides are corresponding with each other. They have the same angles. And then the other sides are interested in, well, we're interested in AP, as we can see. So we can say AP. And it's important that we started with AH in this triangle, so we're starting with AP on this triangle. And then the corresponding side over here is BQ. So we can have over BQ. And then to get the thing that they wanted, we just have to multiply across. So you can see they have AH multiplied by QB. Well, I probably should have written QB, but BQ, QB is the same thing. So if I multiply this up, then we get AH multiplied by QB. Multiplied by QB. So that's multiplying that up. Will be equal to, and multiply the HB up, we'll get AP times HB. So if I multiply the HB up, we'll get AP times HB. Okay. And that's exactly what we were asked to prove at the start. So yeah, and we gave reasons for every geometrical statement that we used.